Good morning to all of you. Today I want to discuss about deadlocks. Deadlock is an important concept in the operating systems. So in the real time also we will come across this deadlock situation. And let us focus on what is a deadlock, how does a deadlock happen, what are the necessary conditions for the deadlock to occur, and what are the methods for handling the deadlock, and how to resolve the deadlock. So let us focus on these issues in today's session. Deadlock is a situation where a set of processes are blocked just because each process is holding a resource and it is waiting for another resource which are acquired by some other process. For example, if any process wants to use any resource, it has to follow in this way. First, it has to a resource, then it can use the resource, and after using it has to release the resource. It has to follow this sequence. If a request cannot be granted immediately, it has to put in the waiting state, and after usage it has to release the resource. So coming to the definition of deadlock, it is a situation where set of processes are blocked because each process is holding a resource and waiting for another resource acquired by some other process. So a set of processes are said to be in the deadlock state when every process in the set is waiting for an event which can only be caused by some other process in the same set. So, for example, if P1, P2, P3, P4 are the processes, these four processes, they are said to be in the deadlock if P1 is waiting for P2, P2 is waiting for P3, P3 is waiting for P4, P4 is waiting for P1 for some event to take place. So here the event may be resource acquisition and resource release. So let us look at some examples where we come across in our real life. So, for example, if you consider this figure, road traffic deadlock situation. Here, if you look at this, assume that the squares, green squares, you have yellow rectangles, you have red, blue. So assume that all these are the cars. So if green cars are coming from top to bottom, and here red cars are going in this direction, and blue cars they are going in from bottom to up. So if the cars are moving in this way, here all these cars, for example, the green car which is touching at the red car, it cannot proceed. It cannot proceed in that. See here, the white lines which are specified here, you can consider them as a road. So none of the cars they can continue their path. They can continue their journey because the cars are they cannot move. So there is a deadlock situation. This is one particular example. And here you can have two trains coming from opposite direction on a single track. And if they meet in the middle, so you are having a single track. So the two trains which come in the opposite direction, none of the train, they cannot, none of the train can proceed in its direction. Okay, that is both the trains will stop. They cannot continue its journey because you are having a single track. Unless you resolve it, unless any one of the train go back, the other train cannot continue its journey. It cannot continue to move. So all these are the examples. So here, deadlocks can happen, can occur either because of same type of resources, or they can evolve because of different types of resources. So same type of resources also the deadlock will occur. For different types of resources also deadlock will occur. So for example, Consider you have a two students. Two students are the two process, and these students wants to note down the points. One student is having a pen, and the other student is holding a book, paper or a book. So here, both the students want to note down the topic, note down the content, but none of the students are willing to release the resource. Okay, so both the students can never write the notes unless, because none of them are willing to release the resource which are held up with them. So student one is waiting for student two to release the pen, and student two is waiting for student one to release the book. So both will not release the resources. So both the students will be held up in the deadlock situation. So this is an example where the deadlock occurs due to different types of resources. And similarly, deadlock can happen because of same resources. For example, we have three tape drives and you have three processes. Each one is allocated with one tape drive. But to complete the execution, each and every process requires two tape drives. So none of the processes are willing to release its tape drive unless it gets one more tape drive. But there are only three tape drives available in the system. So this is a situation where the processes P1, P2 and P3 will be held in the deadlock state because of resources, because of the resource type tape drives. So these are the situations where the deadlock can happen. So this is a situation. For example, here if you look at this diagram, in the operating system, when there are two or more processes that hold some resources and wait for other resources which are by others. See here, the process P1 is requesting for resource R2 and the resource R2 has been assigned to process P2 and process P2 is waiting for resource R1 which is assigned to process P1. So P2 is waiting for P1 and P1 in turn is waiting for P2. So this is a deadlock situation. This is a deadlock situation. And for a deadlock to take place, there are four necessary conditions. If any one of the condition fails, we can say that there is no deadlock. So these are all the necessary conditions. So the first condition is mutual exclusion. Mutual exclusion means one or more resources should be in the non-shareable mode. So for example, printer, it cannot be shared. If all the resources are shareable resources, then there is no point of deadlock at all. So here, in this diagram, you can see that there is a process P1 which is assigned with the resource R1. That is P1 is holding the resource R1. Now P2 if P2 wants to access R1, it is not possible because at that time R1 is already assigned to P1. When P1 is accessing the resource R1, P2 cannot access because R1 is non-shareable resource. So for this resource R1, a deadlock may take place. So this is a mutual exclusion. So at least there should be one resource which is in non-shareable mode. Only one process can use a resource at a time. Next condition is hold and wait. A process is holding at least one resource and is waiting for some other resource. So here the resources can be anything. CPU cycles are the resources, IO, hardware resources, files, all these are the resources. So when to execute a process, it requires a number of resources. So especially in the multi-programming environment, you have multiple programs which are stored in the main memory. So all these processes, they need the resources, and the resources are finite. There are finite number of resources. So here there may be a deadlock can occur because of these resources. If the process wants any resource, and if that resource is held up with some other waiting process, there is a possibility of deadlock to take place. So here the second condition for the deadlocks is here P1 is waiting for the resource R3, and while it is waiting, it is holding the resources R1 and R2. So these two resources have been already assigned to P1, and P1 is waiting for R3. So to complete the execution, the process P1 requires the resources R1, R2 and R3. So unless it gets the resource R3, it will not release the resources R1 and R2. Right? So next, R3 is assigned to P2. So P1 is waiting for P2 to release the resource R3. So here the process P1 is holding resources and is waiting for some other resource which is held up with some other process. So P1 may be waiting for resource R1. So here there is a possibility of a deadlock. So mutually one is waiting for the other. This is a situation. This is a second condition. The third condition is no preemption. Resources cannot be taken forcibly from a process unless the process release the resource. The process has to release the resource voluntarily. Otherwise, we cannot take the resource forcibly from any process. So here, resource R1 is assigned to P1. So P1 has to release the resource R1 voluntarily after it completes the execution. So OS cannot interrupt. OS cannot forcibly take the resource from that process P1. This is not allowed. No preemption. That is the meaning of this. The last condition is circular wait. Here, you have a set of processes which are waiting for each other in a circular fashion. So P1 is waiting for P2, P2 is waiting for P3, P3 is waiting for P4, P4 is waiting for Pn, Pn is waiting for P1 in turn. So you have a circular form, you have a circular wait. So in this figure, two processes are waiting for each other. So P1 is waiting for R1, P1 is waiting for P2 to release the resource R1, and P2 is waiting for P1 to release the resource R2. So this situation is circular wait. So if four conditions are satisfied, then only we say that there is a deadlock. Otherwise, there is no deadlock. If any one of the condition violates, fails, we can confirmly say that there is no deadlock. So all the conditions must and should satisfy. Then only we can say that it is a deadlock. So for example, you can consider that you have a bridge. You want, for example, your river crossing example. You want to cross the river. And on this river, you have a stepping stones. And a person who, that is the job is, the process is crossing the river. So process P1 wants to cross the river and process P2 also wants to cross the river. So and here, how to cross the river? What are the resources it requires? The stepping stones. So you have a stepping stones which are placed to cross the river. Using all these stepping stones, they can cross. And the constraint here is no 2 foots can be placed on the stepping stone. Only 1 foot can be placed. So each and every stepping stone is in non-shareable mode. It cannot be shared. No 2 foot can be placed on the stepping stone. That is very important. So if here in this scenario, if two people wants to cross the river from both the ends, and if they meet in the middle, there will be a deadlock situation. Because why? Because is none of them can proceed, none of them can continue their journey. They cannot cross the river, they cannot complete that action, because both of them want the stepping stone, but it cannot be shared. Both of them are not willing to give the stepping stone to others, so they have to wait. So these two persons will be waiting for an indefinite amount of time. None of them can continue their action. Such a situation is called the deadlock situation. So, for this example, let us see whether these four conditions are met or not. So, coming to the first condition, what is the first condition? Mutual exclusion. So, here, all the stepping stones, which are called the resources here, all the stepping stones are non-shareable. So, the first condition is met. Hold and wait. Second condition is hold and wait. So each person is holding one stepping stone and waiting for other stepping stone. Waiting for other stepping stone. So hold and wait condition is met. Next one is no preemption. So no preemption is here the any person cannot forcibly take the stepping stone from the other one. They need to wait until they release the resource. So if they forcibly take, the other person will fall in the river. So it should not be done. Circular wait. So if the people who cross from this end will be waiting for the people who cross from that end, from the opposite direction. So both are waiting for each other continuously. So since all the conditions are met in the river crossing example, we can say that that is a deadlock situation. So we have seen several examples how the deadlock will happen. What is the deadlock? What is the definition of deadlock? Because deadlock is not desirable to have. It is a problem. We should resolve the deadlock. We should solve that problem. And deadlocks can be described in a precise way in terms of directed graph, which is called as resource allocation graph. System resource allocation graph, RAG. So this graph contains vertices and edges. So the resource allocation graph contains vertices and edges. And here there are two types of vertices here. One is process vertex and the other one is resource vertex. So process vertex are represented with the help of circles. So every process will be represented as a process vertex, and generally we'll be representing this with a circle. Next is resource vertex. Every resource will be represented as a resource vertex. And these resources are of two types. Single instance resource type, multiple instances resource type. So in the single instance, you have only one resource of that type. So here, the processes are represented with the circles, resources are represented with squares. And in each square, if there is a single instance, we'll plot them with single dot. If you have two instances, we'll be increasing the dots. Each dot represents an instance of a resource type. So when you have four instances, you'll be having four dots. So multi-resource instance it also represents a box, and inside the box, there will be many dots present. So if there are four instances, four dots, six instances, six dots, like that it will be. So here, if you look at this vertices, you have process vertex, resource vertex, and you have a single instance and you have a multiple instance. So for example, multiple instances, this you can examples will be registers. Single instance is CPU. Now, coming to the edges, because the graph is a set of vertices and edges, we have seen about the vertices. That is, vertices are of two different types, processes and resources. Now, coming to the edges, we have two different types of edges. One is a request edge and the other one is an assignment edge. So here, if you have already assigned a resource to a process, then it is called assignment edge. Then it is called assignment edge. So request edge means in future, it may want some resource to complete the execution. That is called the request edge. So it may in future, the process may request for a resource type to complete the execution. That is called the request edge. So here the symbols will be like this. So for an assignment edge, the uh, pointer should be from the dot to that process P. The arrow should be like this. So it specifies which instance has been assigned. Which instance has been assigned to satisfy that request. Similarly, request edges means you can have an arrow. You can have an arrow from the P from a process to the square. From a process to the square. So telling that the request can be satisfied by any instance. Not only because when you divide into classes, it means that any printer or any tape drive, it can satisfy the request. So all of them are similar type. Then only it will be the class. Now here, single instance resource allocation graph and you have a multiple instance resource allocation graph. So this is a single instance because the deadlocks can be described more precisely using resource allocation graph. So the whole system, what are the resources available, how many instances are available, which instances have been allocated, what are the requests, everything will be known from this resource allocation graph. So here if you look at this diagram, you have four processes which are allocated to some, you have four processes and to these four processes resources have been allocated and these processes may request for the resources. So everything is shown here. So this is a deadlock free. There is no deadlock here because there are no cycles in the graph. If there are no cycles, then there is no point of deadlock. If there is a cycle, there is a deadlock. So how you can check whether the deadlock is present or not is, if there is no cycle, there is no deadlock at all. If there is a cycle, there is a deadlock. This is a single instance resource allocation graph. And similarly, you have the multiple instance resource allocation graph. So here, if you look at the resource types, as usual, we are having four process types, four circles named with P1, P2, P3, P4, and you have two resources, and each resource type is having two instances. And it is shown here which instance has been allocated to which process. So P1 is requesting for R1 resource, but its two instances have been already allocated to P2 and P3. Similarly, P4 is requesting for P4 is not requesting for any resource, but P3 is requesting for resource type R2, and these instances have been allocated to P1, 1 to P1 and 1 to P4. This is a situation. So here there is no cycle and there is no deadlock. See here there is a cycle but there is no deadlock. Why? Because a cycle is a necessary condition but it is not a sufficient condition. If each resource type is a single, then cycle is a necessary as well as sufficient condition. Otherwise, it is only the necessary condition. In this diagram, though you have a cycle, though you have a cycle, you, you can resolve the problem because if P4 releases any resource, the cycle will be broken. So you can resolve the deadlock. And next, coming for the methods, how to handle the deadlock. There are three methods. One is deadlock prevention or deadlock avoidance. So here, in this deadlock prevention or avoidance, we want that is we want to take preventive actions to avoid, that is not to enter the deadlock, not to enter into the deadlock state. We want to prevent or avoid the deadlock. We want to ensure that deadlock will never enter into the system. Okay, it never enter into the deadlock state. So we must allow the next option is deadlock detection and recovery. We can allow the system to enter into a deadlock state. You can detect it, and next you can recover the deadlock. And the last option is ignore the problem. So we just pretend that deadlock will never occur into the system, and we just ignore the problem, and we pretend that deadlock will never enter into the system. Okay, if at all, if it occurs, you can reboot the system. So these are the different methods for handling deadlocks: deadlock prevention or avoidance. So in both the cases, we should make sure that deadlock will never enter into the system. In the deadlock prevention, we see that the four necessary conditions, how to violate them, how to violate the four necessary conditions. So using some protocol or the other, we need to prevent the deadlock. So similar in the deadlock avoidance, we have a banker's algorithm. So we see that deadlock will never enter into the system. So for that reason, we build a safe sequence. We develop a safe sequence. So safe sequence means in some order or the other, we want to execute the processes avoiding the deadlock. We want to complete all the process in some order or the other. Right? So in the deadlock detection, we have an algorithm which can be detected and what are the recovery actions. So either by process termination or resource preemption, you can recover the deadlock. Last option is ignore the problem. And coming to the strategies to recover from the deadlock, there are two methods to recover from the deadlock. So here, if you allow the deadlock, if you allow the process, if you make the system to enter into the deadlock, you need to check whether there is a deadlock. So whenever the CPU utilization drops down, you need to check whether there is any deadlock. So one first option is you want to kill one or more processes to recover from the deadlock. So by killing the process it will get terminated. Process will get terminated, and its resources can be utilized by some other process, and it can continue the execution. And the next option is resource preemption. You need to preempt the resource from some process and give these resources to other processes which are waiting for those resources. That's the meaning. So while you are preempting the resources, what are the process? From which process you will preempt the resources? You need to select the victim process. Similarly, whenever you terminate the process, killing the process, what does it do? So where does it go? So here either you can have a complete rollback or you can have a rollback to some safe point. So at each and every stage, you need to maintain what are the safe points, so that whenever any deadlock occurs, you can reach to the safe point. So in the next session, we'll see the banker's algorithm. Thank you all.